Okay, let's look now at a simple example um, where we'll start to illustrate this Bodie method. What we're going to look at is actually just a simple RL circuit, just a single inductor and a single resistor. And we're going to take our output voltage across the resistor. So this is VO, this is R, this is L, and this is our input voltage. Again, knowing the properties of the frequency dependent behavior of an inductor, at low frequencies here, the inductor is short, and so the entire input voltage will be across the resistor, and the output voltage will be equal to the input voltage. At high frequencies, the inductor has a large impedance, j omega L. So as omega becomes infinitely large, the impedance here becomes infinitely large, and there will be no current. And so that the output voltage would go to zero. So this is another example of what we would call a low-pass filter. We looked at an RC circuit in the past where we took the output voltage across the capacitor and also had a low-pass filter. So here's an RL example of a low-pass filter. So the transfer function or frequency response is the ratio of the output to the input as a function of frequency. We can use voltage division to get this ratio. Again, these are working in the phasor domain. This would be j omega L and R, and this using voltage division, this would just be R over R plus j omega L. So this would be the frequency response, again, as a function of omega. We'll learn to write these in certain standard forms. I can put this into a standard form by actually dividing the numerator and denominator by R, and I'll have 1 over 1 plus j omega L over R. Or I can write that as 1 over 1 plus j omega over omega p, where omega p here is actually equal to R over L. So in the frequency response here, this term appears as a constant, L over R, or I define omega p as R over L. I just replace the ratio with a new constant. So this is called the standard form of the frequency response, and we'll look at other standard forms as well. But continuing this now, the magnitude response in dB would be 20 log of the magnitude of this, but the magnitude of a ratio is just the ratio of the magnitudes. The magnitude or absolute value of 1 is 1, and the denominator I'll have the magnitude of this function of omega. Okay, but this has a real part equal to 1, and then has a varying imaginary part as, so here's my imaginary axis, here's my real axis. The real part of the denominator here is always 1. As omega increases, this dot is going to move vertically along this real axis equal to 1 line. As omega increases, this point will just move up. As it decreases, it will move down. Of course, there is going to be some frequency omega equal to omega p, and we'll see some interesting behavior there. But back to this, the log of a ratio is the difference between the logarithms. So I have 20 log of 1 minus 20 log of magnitude of 1 plus j omega over omega p. Okay. And since the log of 1 is 0, I'll have 0 minus this, or just minus 20 log of 1 plus j omega over omega p. Okay, so we'll continue this actually in the next video.